Hello everyone, welcome back to our generator protection series. In this video we will be focusing on the unbalanced load protection, also known as the negative sequence protection, function 46 in the ANSI code. This protection is essential for detecting and limiting the unbalanced operating conditions that can cause overheating in the rotor. After covering the theory behind negative sequence currents and their effects, we will move into the testing aspect, where we will demonstrate how to verify the delay time and the backup behavior of the negative sequence stage, and I will also show a few practical testing approaches. So let's get started. So now we will talk about the theory behind the negative sequence overcurrent, which is called 46 function in the ANSI code. So if we have any unbalanced load condition, can result in a positive, negative, and zero sequence system. So the negative sequence components rotates counter to the DC field system and hence produces a flux which cuts the rotor at twice the rotational velocity, and that's why large currents with a double frequency are inducted in the field system and in the rotor body, causing a severe heating in the rotor. So during system faults, the short time heating is a part of interest, and in general it can be said that the large generators have a smaller accepted negative sequence capabilities, and also the heating can be approximated by using the K factor, which equal to I2 divided by IN, all the power of square, and multiplied by T, where the K here is the negative sequence current short time constant, and also it should be chosen with a safety margin of approximately 1.25 in respect of the I2 square T rating. Okay, so the negative sequence current arises from the unbalanced condition in a three-phase power system, explained using the symmetrical components method. So in this theory, any unbalanced three-phase current is broken into positive, negative, and zero sequence components. The positive sequence components represent the balanced load and rotates with the system, while the negative sequence rotates in the opposite direction and causes a harmful rotor heating. The zero sequence flows in the neutral path due to phase imbalances. So these components are calculated from the phase current using asymmetrical component formulas, allowing us to analyze and protect against system imbalance. And here is the mathematical formulation for the I1, which is the positive sequence current, I2 negative sequence current, and I0, which is the zero sequence current, where A here is a constant equal to 1 with a phase angle equal to 120 degrees. So, as we explained, the negative sequence overcurrent is very important protection concept which deals with the unbalanced system conditions. These unbalances are typically caused by the open circuit in the system, like down conductors or mechanical failures such as stuck poles, switches, or breakers. So when one or more phases carry different currents, this imbalance produces a negative sequence current in the generator stator, and this negative sequence current interacts with normal positive sequence currents, creating a resultant effect that induced a double frequency current, typically at 120 Hz in the rotor if we have the nominal frequency equal to 60 Hz, and 100 Hz if the nominal frequency is 50 Hz. So this induced current flows on the rotor surface, leading to additional heating. Over time, this surface heating can cause a significant thermal stress and potential damage to the rotor, making it essential to detect and limit negative sequence currents to protect the generator's mechanical integrity. So continuous unbalanced capabilities, it differs from the type of the generator. So the continuous negative sequence capabilities for both the silent pole and the round rotor machines are listed in the table as shown, and the standard requires here a generator to withstand the effect of the listed negative sequence currents, provided that loading does not exceed the rated kilovolt ampere, and that current in any phase does not exceed 105% from the rated current. So it should be noted that the 105% of the phase current restriction is often more limiting than the negative sequence current. So, for example, for the silent pole generator, the silent pole generator normally have winding in the form of conductive parts spaced across the face of each rotor pole. These are two basic types. The first one is the non-connector windings are isolated on each pole phase. The second type is the connector have a conducting parts that bridges between poles to interconnect the ends of all groups at each pole. So when discussing the generator ability to withstand the unbalanced loading, it's important to understand its continuous negative sequence current capability. So for example, the silent pole rotor, the capability depends on whether the windings are connected. So with the connector windings, the generator can typically handle up to 10% of the negative sequence current continuously, while without this winding, the limit drops to about 5%. Moving to the cylindrical rotors, the limits vary with the cooling and the machine size. So for indirectly cooled machines can tolerate around 10%, while the directly cooled machines have a lower limits about 8% up to 960 megavolt ampere, 6% for the rating between 961 and 1200 megavolt ampere, and 5% for a very large machines about 1200 megavolt ampere. So it's worth noting that the winding, also known as a damper or a squirrel cage winding, is used to oscillation and also to help stabilize the rotor winding during the transient conditions, improving the machine's ability to withstand the unbalanced stresses. So now we will talk about the short time of the unbalanced current. So the standard requires that the generator withstand this unbalanced fault conditions that result in the I2 square T duties listed in the table shown in our presentation. So this limits assume that no heat dissipation in the critical rotor structure and are considered valid for conditions lasting up to 120 seconds. So the standards note that the machine subject to I2 square T duties up to 200% of the pre-described limit, which will experience a varying degree of damage. So the standards also require that the generator withstand unbalanced faults at their terminals, including effect of the DC component of the fault current and post-trip decay current. And this DC component adds a significant heat to the rotor for a face-to-face fault as the generator terminals. So both the continuous and the short time capabilities of directly cooled machines are sharply reduced from those of indirectly cooled machines. So for the indirectly cooled machines, the heat generated in the windings must travel through the winding insulation to reach the cooling medium in the air gap. But in the directly cooled generator, the channels are provided in the stator or the rotor slots to allow a direct contact between the heating producing winding conductors and the cooling medium. Therefore, the negative sequence current capability is expressed on the direct cooled machines higher kilovolt ampere pace, and the per unit negative sequence capability is much lower. So the negative sequence relays also are available in electromechanical and electronic models with adjustable time current characteristic intended to match the generator I2 square T capability. So the first type is the electromechanical relays, which are insensitive with a minimum I2 pickup current in the order of 60% of the rated generators. Because of the poor sensitivity, this relay is provided only a backup protection for the unbalanced faults and also normally have two set point, an I2 pickup and a time dial setting. On the other hand, the electronic relays are more sensitive and they are detecting open phases and negative sequence currents down to the continuous I2 limit of the generator, and also the time current curves are derived electronically and match the machine I2 square T characteristic exactly. The time dial calibration on most electronic relays are in the terms of K, where K equal to I2 square multiplied by T. So many of the electronic relays have an alarm feature that can be set to alert the operator of unbalanced condition approaching the trip setting. The relay also has a maximum trip delay adjustable from 10 to 990 seconds in 10-second steps. When the I2 current exceeds the trip threshold setting, the relay begins to accumulate the I2 square T and initiates the maximum delay time. A trip output occurs when the accumulator reaches the K setting or when the maximum time delay times out, whichever occurs first. The relay characteristic flattens above 2 per unit, as you can see from our graph here, which means 200% current, and this delay is about 0.24 second is necessary to allow the primary fault detection relays in the plant or at the switchyard to clear the unbalanced fault without tripping the generator. The memory feature of this relay allows for 250 seconds to empty the accumulated I2 square T from the value just below the K setting of the relay. So in summary, we have two main types of negative sequence relays, electromechanical and electronic. And in summary, the electromechanical relays are less sensitive and mainly provide a backup protection due to a higher pickup threshold, around 60% of the rated current. In contrast, the electronic relay are much more sensitive, matching the generator's thermal I2 square T curve and detecting low-level imbalances and offering features like alarm, like K-based time settings, and the memory of delayed reset. So this memory ensures a quicker response if the fault appears or reappears before the rotor fully cools and improving the protection effectiveness. So as you can see here, how to test the unbalanced load protection or the negative sequence overcurrent protection named 46. So this function protects the rotor against thermal overload due to unbalanced load, and it can be tested using the overcurrent test module or alternatively using the test sequencer test module and the fault calculator. So when using the overcurrent test module, the test object definitions has to be configured accordingly, and for better distinction of the various overcurrent REU function in the test object, you can rename the new function to unbalanced load. So the settings are performed in the negative sequence fault group, and all other fault groups are deactivated. The unbalanced load tripping characteristic is manufacturer specific and has to be added as a new standard characteristic for testing. And the table shows here the definition of this characteristic curve in the test universe software. So as you can see here, here is the unbalanced load protection parameter setting of the relay. So we have the asymmetry factor K equal to 5 seconds. We have the maximum permissible unbalanced load I2, which equal to 7.3%. The delay time of the warning stage equal to 20 seconds, and the I2 double greater equal to 55% with the time delay equal to 3 seconds. So here is the manufacturer equation as we explained. So the trip time equal to K divided by I2 over IN all the power of square, where T here is the trip time, K is the asymmetry factor, which equal to 5 seconds in our parameter setting. I2 is the actual unbalanced load current. IN is the nominal current protection. And here is the general Omicron equation for the IEC normal inverse. As you can see, here is the trip time equal to A multiplied by TD plus K1 over M all the power of P minus Q plus P multiplied by TD plus K2. And here is the T representing the trip time. M is the multiple of the pickup value. K1 equal to K2 equal to B and Q and equal to 0, and B here equal to 2. So the resulting equation, the trip time will be equal to A multiplied by TD over M square. So by equating the both equations, the Omicron equation and the manufacturer equation, and inserting the protection parameters as you can see, so we can equating the two equations, and we have some given values between two brackets as you can see from our parameter setting. Then we can calculate the A constant here, which equal to 187.652. So if we open the OCC file, for example, for the Siemens 7U M621, and you can double click the test object, you will see here the unbalanced load, which is the overcurrent customized curve. So we have here the relay parameters, which is non-directional, and here is the tolerance of the current and time, 3% of the current and 5% of the time as a relative one, and we have also absolute tolerance. Then if you click the element tab, here you will see the two stages, which is I2 greater and I2 double greater. So the I2 greater, which is renamed as unbalanced load, and here is the pickup value, and you can see also the trip time as a definite time in this case, and it's non-directional. So you can see also the A constant, which we are calculate this constant by using the equating the two equations, the manufacturer equation and the Omicron IEC standard inverse equation. So you can get this constant value, and then you can get at the end of the day you will get the characteristic of the first stage, which is starting by 0.73 as a pickup value of the I greater stage, and limited by the second stage, which is the I double greater at 55% of the nominal value. Also, you can see here the second stage, which is a totally definite time, as you can see at 0.55% from the nominal value, and with a trip time delay equal to 3 seconds. Then simply you can click OK. We will get back again for our presentation. So here is how to test the unbalanced load protection, which is 46. As we explained the element in the overcurrent REU file. Also, you can see the equations of the first stage and the second stage. Accessing the curve management here, selecting the standard IEC normal inverse or a user-defined or a customized curve. And also you can select the key factor, the pickup value of the I2 double greater stage and the delay time of the I2 double greater stage, and also you can rename the new characteristic curve. It can be selected freely as you like, and then you can adapt the values according to the preceding table. Then let us move forward to the next step. So here is the local hardware configuration to test this kind of protection relay. As you can see, we have 6 current output must be mapped. The current system A for S1, current system B for S2. Also, we need a start signal must be mapped to the CMC binary input. And also, we can use the voltage transformer circuit breaker tripping, or the VTMCB tripped signal must be wired to the binary input of the protection relay from the binary output of the CMC. And here the first test, how to test the pickup and the drop-off value of the I2 greater stage. So in total we have both ramps. So the ramp 1, we will use the binary trigger start from 0 to 1, and we will ramp up the current from 80% of the standard or the setting value up to 120% with a specific delta size, as you can see, and we are expecting the nominal value to be 73 milliampere as per the relay parameter setting. And here is the tolerance, which is 3%, depends on the relay technical specification. In ramp 2, we will ramp down the current from 120% to 80% to get the drop off value. And here is the assessment of the ramps for ramp 1 to get the backup value and with the start condition from 0 to 1, and ramp 2 to get the drop off value, which is 95% of the expected nominal value of the parameter setting, and the trigger condition to be the start changing from 1 to 0. Also, you can check the calculated assessment as which is the drop off over the pickup, so which is expected to be 95%. You can get also the reset ratio. And in the detail view, as you can see here, the analog output, there is a phase shift of 180 degree between the current on side 1 and the current on side 2 has to be set here. And also you can simulate the VTMCB trip signal to block the under voltage protection function for all ramps. So when testing the unbalanced load protection or the function 46, we need to focus here on the verifying the delay time of the I2 greater pickup warning stage. So normally this test is carried out by exchanging the phase angles of current 2 and current 3, which creates the desired negative sequence condition. However, there are several other testing methods available using the general negative sequence equation, allowing flexibility depending on the test setup or the relay type. For instance, turning one phase current off will produce a negative sequence current of approximately 33% of the remaining phase current, while turning two phase off increases it to about 66% of the remaining phase current. It's also important to remember that the 240-second reset time, which ensures that the protection element returns to its normal state after the unbalance is cleared, and this reset time should always be considered when planning and timing your test sequence. So as you can see, we are using the test sequencer here. State number 1 is the normal operation, which means the current will be the rated secondary current equal to 916 milliamp for 10 seconds, and without any binary trigger needed in this case. And the state number 2, we will inject 1.05 multiplied by the current setting for the negative sequence, which means 76.65 milliamp, and the time to be 1.5, the expected trip time, which means 30 seconds. And state number 3, which is the post fault. And now you can measure the warning time of the stage from state number 2 up to the trip signal or the warning signal of the stage number 1. So you can see here the expected trip time is about 20 seconds, and here is the allowed tolerance for the trip time, which is 200 milliseconds plus or minus. Then you can assess the time measurement values. So here is the third test, which is testing the unbalanced load characteristic. So in general here, you can test trip time. So the pickup and the drop-off test here is not required. Also, you can define the value here to be I2, which is the fault type selection. And this test point also selected in a way that the test times are not too long. And also you can see here in the fault time, there is no load current injected, and the absolute maximum time to be 300 seconds, which to be longer than the trip time of the second stage. Also, we have the thermal image or the enable reset, so it can be enabled manually, which means the test module can be stopped after each single test points and give you a pop-up message to the user to reset the thermal image. And we will use here the trip contact as a trigger condition. Thank you, and stay tuned for the next video.